And today we're going to cover a classical method called subset selection. So first of all, what is model selection? Okay, model selection is the task of selecting a statistical model from a set of candidate models. Okay.
Can you just make sure the mic is on, because this thing is kind of quiet.
Yeah.
Thanks.
Thanks for the reminder. Okay, how does it work? So basically, suppose that we have data. For example, y, x1, x2, x3, xn. And then there will be a bunch of combinations of models with all these variables, right? Like y equals beta 1, x1, y equals beta 2, x2. And also even more combinations, probably with everything. So, what we want to do is to choose which model is the best to represent the correlation of the data. So, how many combinations are there in total?
Be like 2 to the power of the number of variables?
Yes. So 2 to the n, number of models. So we're going to cover, if we look at all these models one by one, that's going to be quite computational intensive, but that is a choice, of course. But the idea of subset selection means that we need to follow some steps to choose the right subset that we want to look at so that we can take kind of shortcut to test less models, but still choose the relatively best model within them. So then when it comes to subset selection, so there are two main things that we want to look at. First of all, which subsets. And then what criteria. Oh my god, my handwriting here. Hopefully it's readable. Okay, so before we go into the steps of choosing the subsets, we're going to talk about the criteria first. There are multiple classic criteria to determine whether a model is good or not. First of all, there is one criteria called a Kaike information criteria. I never remember the full name of it. It's usually called AIC. So this is an estimator of the relative quality of a statistical model. Looks like this. Okay. So last time Alan talked about cross-validation. Hopefully everyone still remember what that is. So for that one, you take one model and then you divide the data set into separate folds, and then you regress on part of the data and then test it on the rest of them. So in that case, you're going to go through different folds, and then it's going to be a bit computational intensive. But with AIC, it's the other idea of using just one metric to evaluate this one model. So it's going to be faster. And the idea here, so there's no need in this course to remember the formula. We need to kind of get what it means. So K is the number of parameters. And L hat is the maximum likelihood value. So the maximum likelihood value basically tells you how good the model is. So you can see that as the maximum likelihood value increases, the AIC would decrease, and as the number of parameters increase, the AIC would increase. So in the end, this whole thing is smaller. So the smaller the better. But you can see that there's a balance. If you still remember the bias variance trade-off, so it's like as you increase the model complexity, the model's prediction is going to be better and better, but there's the risk of overfitting. So when you increase model complexity, it's not always good, so there's like a trade-off of having the right amount of parameters versus having still a good prediction. So, so this whole thing kind of is the trade-off. Like, if you increase the parameters too much, the IC will still be too big. But if, in the meantime, if you have too few parameters and the prediction, the maximum likelihood value is not that big, then it's still going to be not ideal. So, and then for linear model, this can be simplified. Okay. Where's all these mean? N is sample size. And RSS is what we covered before, is the residual sum of stars. And then K again is the number of parameters. hat on sigma here as well. And sigma hat is the estimate of variance. Okay, and this actually looks very similar to our next metric, which is called malloc-CP. So malloc-CP it reduces the RSS while taking into account the number of parameters. So it's the same idea as AIC, right? The trade-off of complexity and predictability. And it is equivalent to AIC for linear regression. Proportionally. Okay, how does this look? They're similar. It also contains RSS and K. So you can see these two metrics are proportionally equivalent, right? And how does this one work? So still, we want the RSS to be as small as possible for the model to be good enough. But also, we don't want the number of parameters to be too much. So we also want K to okay, probably that's not right. So how do I explain this? So when we want the RSS to be as small as possible, it's likely that K would actually increase. So there's this trade-off again. And it's the same idea as AIC, right? And then actually our next metric look very similar too. It's called Bayesian information criteria. Also called DIC. So this one is also similar to AIC, but with a different penalty for parameters. This is how it looks. So here instead of, so for AIC, this penalty term is 2. Yeah, here. It is 2. But then for BIC, it is ln. So that's a different penalty. Actually, it's usually a bigger penalty compared to AIC. So also this is smaller the better.
I'm sorry, can you repeat, what are the differences again?
So for AIC here, so this term is the same for AIC and BIC, but we have a penalty here for K, and for AIC it is 2, but for BIC it is this ln.
Okay.
Okay. So it has a bigger penalty. And especially when, so n is the sample size, so especially when n is very large, this penalty is going to be very big. So, so especially on models with more variables. Okay. Any questions about how these 3 metrics work? Everything clear? Okay.
Can you describe what you mean by penalty?
Okay. So usually we want to evaluate a model, like how good it is. So before we all talked about how well it fits the data. So first of all, we want to reduce the bias and variance trade-off. We want to reduce the bias. But then when we increase the complexity of the model, or like we add more parameters into the model, it's likely that we're gonna introduce more variance. So the bias variance trade-off looks like this. Something like the error of total error of the model and model complexity. So we have, as we increase the model complexity, we're going to have less bias, but more variance. So the total error would look like this, right? So usually there's 2 terms. So all these 3 metrics work in a similar way. There are 2 terms, and then one of it measures how well the model does in decreasing the bias, and then the other term controls something related to the number of parameters. So this term is usually the penalty for this, because for example, for BIC it's like smaller the better. So when it comes to the optimal, it's like selects one that tries to decrease the number of K, which is related to how this penalty term works. Is it clear?
Can you explain the all hat? Also, I'm not quite sure what's happening. Like, can you connect it to the, is it related to the bias trade-off?
Yes, so L hat actually in a linear model is the OLS, the least square. So it's like, it actually represents how well the model is in terms of like how little the bias there is. But this general thing of L has the maximum likelihood value. This is like a generalized term for like all models, not just the linear models. But for linear models, you can just interpret this as like the ordinary least squares. Yeah. Any other questions? Okay, so there's actually a fourth metric that is related to what we learned before. Adjusted R squared. So what was the R squared look like before? Okay, wait, going too fast here. So this is what the R squared looked like before. So it's a value between 0 and 1, and it's better if it's bigger, right? But this one here only covers, let's say, how well the model covers the variability in the data. But we also want to take into account, like same as before, in the other metrics, we want to take into account the number of parameters and want to penalize it in some way. So the adjusted R square has an additional term. So again, n is the sample size, and k is the number of parameters. So let's see. Who can tell me what happens when we increase the value of k, the number of parameters? What's going to happen to this term, this whole adjusted R squared? So what's going to happen to this denominator here? It's going to decrease, right? And then this whole thing after the minus sign is going to increase, right? So then the adjusted R squared actually decrease. So we want the adjusted R squared still to be as big as possible. So in this way, when we increase the number of parameters, there's like a penalty again, right? So again, this model performs like a trade-off of maintaining the RSS versus TSS, this term here, as good as possible. In the meantime, we want to have like a right amount of parameters, not too many, so that there won't be overfitting. Okay. Any questions about this?
Maybe you can just repeat the final thing you said. You don't want to increase the number of parameters because of overfitting.
Mm-hmm. So like how that works in adjusted R squared. So we want this to be, so bigger is better. So we want how do I explain this? So in terms of the number of parameters, when you increase the k, the adjusted R-square would decrease, so then it's not going to be optimal anymore because it's, since we're going to choose the bigger ones, if we have too many k, it's going to be too small, right? So that's how it gives you this kind of balance.
And maybe you will address the balance. How do we determine where the model is appropriate, but it's not overfitted?
So I think this metric itself would give you the balance point because like, how do I explain? Like neither of these terms are going to go to an extreme at the very optimal value that you choose. So it's not going to be like, if you don't have this term, then we're going to just choose like whatever the best of this term, right? But then when we have this, they have like a balance by themselves. Does that answer your question?
Sure.
Okay. Okay, so then we're going to discuss how does these different metrics compare to each other. They have a similar idea, but like under what cases are we going to choose to use them, right? So first of all, just the R-square versus ASC, CP, and DIC. Oh. So basically, R-square tells you how well does your model explain observed data. And AIC, CP, BIC tells you how well will your model fit new data. So for R-square, so for R-square, usually it's normalized between 0 and 1, not usually. It's always between 0 and 1, and it is the higher the better. And then for ASC and CP and BIC, it's always lower the better. Okay. So they all, as we mentioned, penalize more parameters. R-square is usually more popular. But not as use statistically. Right. Okay. So that is the difference between R square and all the others. Because they basically work differently. For R square, it mainly focuses on how you capture the variability in your data. But for ASC, CP, and BIC, it has the term of the maximum likelihood value, which actually directly look at the bias that your model is. So that's how they're different in this way. And then for ASC, CP, and BIC, oh my god. How do we choose between these? So ASC and CP are proportionally the same versus BIC. Their main difference is the penalty term on the number of parameters, right? So BIC is argued to be to identify true model as n approaches infinity. So when you have a very large sample size. But AIC minimizes selecting a bad model when you have a small n. And also people who like to use AIC would argue that there's actually no true model, like your n is never big enough, right? So I would say AIC is a more conservative way to use to evaluate this model. But when you have a very large sample size, you're confident enough, you can choose to use BIC. And of course, cross-validation. So of course we can also directly estimate test error with cross-validation. So cross-validation, as we mentioned, it can be very computationally intensive. But right now, it's not that case anymore. Like, it's still intensive, but computers nowadays can calculate this much faster. So this could still be one of the choices. And actually, cross-validation is always the most accurate way because it directly tests the test error versus all these other metrics. They try to take a shortcut of using a metric to represent the balance of variance and bias trade-off. So it doesn't look at the test error itself. It doesn't actually regress the model on certain part of your data set and then actually test it on another subset. So they're very different. The cross-validation is the most accurate, but it can be computationally intensive. Okay. So is everyone clear about all these metrics or criteria of evaluating, like once you have a model, how do you evaluate whether this model is good enough? Is there any questions? Okay. So then we're going to move on to talk about the steps of selecting the subset. Like which subset are we going to look at? Not all the potential combinations. There's going to be 2 to the n. Number of combinations, if that is too big, how do we select some subset? So it is called stepwise selection. So as we talked about larger decay, more combinations. Those variables. So this is the number of possibilities, right? 2 to the k. And in stepwise selection, there's forward and backward stepwise. I'm going to give you a demonstration on the forward. So what are the steps? Suppose we have, okay, before I go into an actual model, let me just explain like how the general steps are. So first of all, we choose a model with no predictors. So start with nothing, and then for so we move from k equals 0 to k. For each step here, we add one additional predictor. So one at a time, and we test all remaining predictors. So one at a time, we choose from all the remaining predictors, like choose just one that is the best. Select the best as having the smallest RSS or biggest R square. And then we have, like, at each step, we have one best model. And then we have all these models. Between them, we're going to select another best, which is the best overall, based on selection criteria. So these selection criteria here are going to be the ones that we just mentioned, like AIC, BIC, CP, or adjusted R square. And like within the steps between them, I'm going to use RSS or R square. Okay, so I'm going to demonstrate how to actually apply this with a small example. Suppose we have this model here. We have y, x1, x2, x3. So, step one. Where do we start for forward stepwise selection?
Zero predictors.
Yeah, and then what are the different candidates that we're gonna test on for this step?
The intercept.
Yeah, so that is like even before the first step, right? You have this. Yes, so for the first step, you have the model with no predictors, and then we start to go through like one additional predictor at a time. So what are the models that we're going to test on right now? So maybe these three models, right, where we have just one predictor. Suppose that we have an R square for each model. For the first, let's say it's 0.8, for the second is 0.9, and for the third it is 0.7. So then which one is the best one within this step? Mm-hmm. So we're going to choose this one, right? And then, what about the next step? What are the models that we're going to test on the next step?
Are we going to include any constant terms in the equations?
Yeah. I suppose it's included. I just don't want to like add too many things here, but
Okay.
yeah.
So does it affect the R square?
Actually, it will. You can also test on whether you want a constant or not in this model.
Having a constant gives us the flexibility of not passing through the origin.
Yes, yeah.
So if there's a constant, then the R squared value can differ a lot, I feel.
Yeah, so so adding a constant or not is similar to like just adding one additional variable, I would say here. So you can test that.
But then adding additional variables could contort the actual shape of the curve that we're generating here. But adding a constant won't change the shape, just the location of the curve on the Cartesian plane, if we're just imagining Cartesian plane.
Sorry, can you repeat that?
So adding a constant won't change the shape of the curve that we're defining here,
Mhm.
but adding another variable might change the shape of the curve.
Yeah, that's true.
Yeah, so that would affect R square differently, right?
Yeah, so when you're regressing the model, usually I think it's the default of having a constant considered. That's like included in when you're doing a regression.
So basically the bias term.
The constant, I would say, the constant you're talking about is the intercept, right? It's not
Yeah,
the
that is
bias.
the intercept.
That is different.
Okay.
Yeah.
Okay, so are we going to include when we try to, you know,
Yeah, I think when you're applying it to R, it should be like a default, but you can also change it.
okay.
Yeah. So for the next step, what are the candidate models?
Y equals beta 2x2,
Mm-hmm.
and then you add beta 1x1.
Yes. Another candidate would be beta 3, x3, right? So for this one, let's suppose that R square is this. So 0.91 and 0.94. Which one are we going to choose at this step? Mhm. Then we can move on to step 3. Start with this best model that we selected from step 2. And since we have only 3 variables now, it's just going to be beta 1 is 1. So this would automatically be the best choice in this step. Okay. So what next? What are we going to do next? According to these steps?
Select the best overall.
Yes. So between all these 3 best models, we're going to select which one has the highest adjusted R square or AIC or CP or DIC, whichever you want to use. Okay?
I'm sorry, for step number 3, what I have written, it says select best overall based on selection criteria.
Okay, so these steps here are actually like the steps within here. And then the step 3 here is the step of after all these best models are chosen in each step, that step 3 is what we do here. Any questions on this?
What's the R square percent, the last one?
Well, there's no assumption on that, but we can assume that it's anything, because this is just an example. Let's say it's 0.93 or something like that. Okay. Actually, wait. I think it's going to be like something like 0.95. I think Because once you increase the model complexity, I think the R square can only get bigger.
But as you said before, there's a trade-off between the number of parameters and the value of R squared. So how do we find out the inflection point where it turns? So where the thing that you were talking about, finding the optimal
Yes.
value of parameters so that the R squared value is the highest.
Yes.
So yeah.
So you're asking like, why are we using R square within these small steps, right? Instead of like the adjusted R square.
Basically, yeah.
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 So the reason why we use R square within these steps, because every time we're only comparing the models with the same amount of parameters, right? So in that case, the number of parameters is not a variable anymore. Like it's not gonna make a difference on how well the model performs. Even if you have the adjusted R square, that term is gonna be the same. And in the end, we have all these best models within each number of parameter group. So then in this final step, we're going to use all these parameters that are that consider this trade-off between the number of parameters and how well the model does. So yeah, that's basically why we're using these different metrics. Okay. Any questions on this?
Can you explain to me step number 3, why? I'm just sorry, where does step number 3, like what are you doing in step number 3 right here?
You mean like this one here?
Yes.
So actually step number 3 is like, so for each step you increase one predictor, and then for step number 3 you want to increase another one. So based on this model, we
Okay.
increase, but now there's just one candidate, so we don't have other models to compare. So this is just automatically what
Okay.
we choose. If there are like even more, there's going to be like more steps. Okay.
I have a question.
Yeah.
You said that R square for the model step 3 will always be higher than the other models, right? Or
Yeah, I probably need to check that, but I think I have the impression of like R square is always going to be higher.
okay. So
Yeah.
we basically choose between based on AIC, BIC, or CP.
Like in the final step, yes. Like between all these models that are like the best candidate within their type. Yeah, so in the end, we're going to use these because they have different number of parameters, and we need to consider that as a factor. Okay.
And for step 3 then, so for each step we add one parameter,
Yes.
and then for step 3, let's say we have 10 different options to choose from. We're still going to look at whichever one has the highest R squared or lowest RSS.
Yes.
Okay, thank you.
Okay. So this is forward stepwise. There's of course backward stepwise as well. We're not going to go into like details anymore since you guys already know the idea of these stepwise selections. So it's basically the same as forward. But it starts with the model with all the predictors. And Forward stepwise is like starting with nothing, but backward is starting with everything. Yeah.
Is there a benefit to doing one or the other?
Usually I think sometimes we just do both because one or the other, they both have the risk of neglecting some of the subsets, right? Neglecting some model that might be actually the best. So they actually go through, sometimes they go through the same subsets, but they can also have some disagreement. So usually we do both. So I would say there's no preference between them. Yeah. Oh, and there's one thing very important to note here. All these metrics that we're using, R squared and all the adjusted R squared, ASC and CP and BIC, these are for determining whether this model is good or not. And some people might say that why not use like p-value, statistical significance of the model. And please remember that is very wrong to use in this because the statistical significance level tells you what the model says instead of how well the model performs to fit the data. So it's really two different separate things. They might be related in some way, but when you're doing model selection, remember not to use the statistical level of significance. Okay? Probably not here. Avoid stepwise with p-value as criteria. Okay? Yeah.
Isn't p-value used to check significance of individual parameters?
Yes. Yeah.
So it's not an overall model while steady state, right? Anyway.
Yeah, that's true. Some people might just like check on the different p-values and see like which one is more significant to use it as like a reference, but just don't use it as a reference when you're doing model selection. It's more in the model interpretation. Yeah. Okay, so we're done with the theoretic part for today. We're gonna now get into how to perform this stepwise selection in R. So these are the packages that we're going to use for today. ISLR is a package with, I think, some data sets that are usually for tutorial, and then the stats have, these stats and mass have some functions form criteria. And now we're going to use today we're going to use a data set that is called credit. So look at what does it look like? So this is a data set that is about credit cards. So I think it's for like each individual. There are some variables about like how many cars this person has, the age, years of education, and everything. So, first of all, we want to identify the variables that we're going to use. So we want to regress on the value of balance. That is going to be our y. So all the others are going to be the candidate x's. So we want the names in the credits that are not within this vector. So we want to exclude the column of ID and balance so that we get all the candidate variables. Okay. And now let's try to perform a step forward. Regression. First, we have, let's define some vectors to store all the models.
Yeah.
Yes?
Do you mind increasing the font size?
Okay. Let's see how to do that. Is that better?
Maybe a little bit.
Even more? Like this? Can everyone see it? Okay. So these are the vectors to store all the models and all the selected variables. And you'll find out how to use them very soon. So we're going to loop. This is how we perform all the steps that we talked about. And I should probably just look here. Okay, let's just. So the number of steps is the number of variables that we have, right? And here we're looking through 1 to the number of variables, number of the credit names that we extracted, okay? So within each step, we have so within each step, for example, here, we already have x2 is our selected variable, and we want to test on the rest of the variables. And what we do in R is select the names that are not in selected variable. Okay. And then within each step, we also have a best model to be chosen. So there's vector to store what it is, and then something to store the best R squared. And then the best names. And within each step, so the outer for loop is for these steps, and then the inner for loop would be for these individual models that we test on. So now we have another loop. We test on all the available variables. So basically, this step is to write the formula of like x1, beta 1 x1 plus beta 2 x2, which is for later in the regression. And what this paste function does is actually putting some strings together, and this collapse here. So let's see. So putting strings together, so how we use it would be, for example, some string. And collapse is what is the connection that we want between the strings. So for example, if we want also plus here. Wait. Maybe this is how it works. Yes. See how it works? Like you put a vector of strings, and then whatever you want to put between them, and then it will give you a new string that's like the combination. So that's what this line does here. It has all the variable names, all the available names, like actually just one available name choosing from like all the available variables for this step, and then connect that with the already selected variables. And then there's another function called formula that can transfer a string into a formula. So the formula, we want it to be like this, like where you rest on a balance, and then you have all the variables hold on the other side. So this formula is for the LM function in stats. The data that we're regressing on is credit. Okay. R square would be in the results. What's going on here? Is it working? Okay, where are we at? Okay. So now we have, we're in the step of looping through all the candidate model at each step. And what are we going to do right now? According to this. Where are we?
Step 2, we have to test which one is best and just keep that and then go through the loop again.
Yes. And how do you choose the best model within the step?
Best R square.
Yes.
Highest R square.
And how do you do that in R?
If R squared of the current model greater than best R squared, keep current model.
Yeah, exactly. So if the R squared at this step is higher than the best R squared that is stored, we replace the best R squared with this R squared. Okay. And we also store the best name in this step and the best model. Okay. So now we can get out of the loop. We're getting out of the small loop. And what do we do now? So we add this best variable that we selected from the small loop into the bigger model, and then go to another loop, right? And here we want to store all the models. So adding this best model within this small step into the collection of all the best models in the end. Okay, so this gives us all the models. This whole loop here will give us all the models that are in the red circles. And what we want to do is to test them on the metrics. Okay, I hope I didn't make any mistake. Okay, great, it works. Let's see what's going on here. So we printed yes, here. Now we can see what's going on within each step. So in the first step, we chose the variable rating, and then for the next step, we chose the income in addition. And then one more variable is chosen for each step. And then all these are tested with the AIC. And these are the AIC values. We'll see that the best one is probably this one. This one here. It's the smallest, right? Okay. We can also apply this to other metrics. This is the value for BIC. Which one is the best? Is it? I think this one is the best. So there are chances that these criteria won't match with each other. They might have some slight disagreements. And then there's the adjusted R-square. Okay. So the adjusted R-square is in the summary already, so we can just pull it out. Which one is the biggest here? This one, right? I think. Yeah. So there are slight disagreements between AIC and BIC, but AIC and adjusted R-square agree on the best model. So it really depends on which metric you prefer to use according to how your data is like and what are the models you're choosing, right? So let's see. So this is how we do the step forward regression manually. Is there any questions on this?
Can we easily use some like function in the R?
That's exactly what I'm going to mention. Yeah, so this is just to tell you like how this works. But of course there are built-in functions. The built-in functions are, let's see. First of all, we need to like concatenate the variables together. So now we want the credit names and the balance. And the model is the linear regression. So this tilde period just tells you to use all the variables to regress on everything. That's like a abbreviation here. And there is model AIC. This function is called step AIC. So you put your model here, and you can choose the direction. So we're going to use both here. Let's see what's going on. Oh, I didn't run these lines. Here we go. So this tells you what is going on in the built-in package. So it starts with a model like this, and then it tests how the like sum of square, RSS, and AIC change when we take out each variable. And then in the next step, I decided to take out ethnicity, I think, because this gives you the best AIC. And then, so in this kind of both forward and backward regression, I believe this package would do like testing, like removing one variable and also versus adding variable, like the different effects at each step. So then for each step, it tests on the effect of either removing or adding one of the remaining variables, and then choose the best model accordingly. So after going through all these steps, I think this is how it ends. Like none of these changes could decrease the AIC anymore. So then it comes to the best model that is identified. Okay? And we want to do BIC. It's going to be, we still use the step AIC function. There's just one parameter that we can change, which is the K. Remember, that is the penalty term for the number of parameters. That is the only difference between AIC and BIC. So now we change this to log n. That will give us the estimation according to the BIC. Do these agree on each other though? Not really. Yeah, that's how these different metrics are. Any questions on this? Okay. And note that if we want to do like a forward regression here, we're going to do something else. It's not just changing this direction to forward. Actually, what we do is we need to define the start and end. This is the model with nothing. So we change the direction to forward, but we want to define the scope. Lower is the model that we just defined, the model with nothing, and the upper is model with everything. Okay.
What is the very final end? If you could scroll out a little bit, separate, what is that, SCP with comma?
This
With
one?
nothing. Okay, thank you.
Yeah. This just tells you there's no separation between the strings that we want to put together. Okay, so this will give you a step forward regression. Where did this start? Here, yeah. Test on all the candidate variables and then adding one at a time. And the ASC value will increase in every step. Okay? Any questions?
Could you explain the balance thing when you define the model? When you define the linear model, the lm command?
This one here?
I can't see which one you're pointing out to.
Oh, sorry. Sorry. There it is.
Yeah.
This one?
This one. What's the balance thing?
So this is how the linear model, this LM function works. You need to write the function, the formula of the model that you want to regress.
Okay.
So balance is the name of the Y that we want to, yes, this is the name of the variable.
Right. And what does the one stand for?
So regressing on one means that it's an empty model. I think it's only with an intercept. Let's see.
Because you did regressing on, I think, dot, which means all. in the model that you find about that.
Here?
Yeah, that's
Yes, like dot means like you're regressing on everything.
everything,
And
right?
then one means that you're regressing on nothing.
Or nothing.
Yes,
Oh, okay.
I think it is. Let's see the summary of this model. Yeah, there's just the intercept. So that's how it works.
Oh, thank you.
Yeah. Any other questions? If not, this is what I have for you today. Model selection, subset selection. Yeah. So I guess we can end the class earlier today. Probably I'm going too fast, but hopefully you all are clear about this. Okay. So that's it for today. Thanks a lot for your attention.